So this part is very important. It's about the exam. And if you take a look at the, I believe it's already posted on at the modules. And there's the practice exam here. And I'm going to move this part to the homework and solution part and code part. And then you will see I also move the midterm exam cheat-sheets, midterm exams review PDF here. I'm going to move this practice exams to here as well after this class. And if you take a look at the practice exam, I'm going to change the questions, the number of questions this time. But if you take a look at the practice exams, we have like 10 questions. That's a lot. But in the actual exams, it could be like 4 questions. Got that? And it's just like 4 questions, and then for 50 minutes. We would definitely have 1 question looks like this, because this one is the most easier one. And it can like take 5 to 10 minutes to finish the question 2. And for the other question, I would choose like 3 questions from the other questions, but I would change the number a little bit, not just the original one versions of this one. So what you need to do is to get practice on these questions, and you will find out that the question is pretty similar to your, or it's just copied from your homework question. So which means that if you know how to do the homework, and then you know how to do the practice exam, and you know how to do the actual exam, so there's not so much work to prepare for the exam this week. You just need to know the homework questions and the solutions to the questions should be already posted. I'm not sure if the TA posted the solution yet. Yeah, you get the solution, homework 1 and homework 2, and I believe the TA is posting their homework 3 and 4 this weekend or this week. And there's one question here that just go to there. The questions, there's one new homework here, and this homework is pretty easy, and it's the homework 4. It's still on the Friday, but it's still easy. This one, there's just 1 question this time, because next week is the midterm. And I just post this homework because I want you to practice on this question. And there is something similar to this on your exam as well. It's about the composite trapezoidal rule and the composite Simpson's rule, and they should be on the exam as well. Just apply the rules, and then to get the approximations, you don't need to do anything about the irritants. Just apply the rules, the formula, and that's it. And today we are going to talk about a new topic, and then it is also on the exam as well. So let's take a look at this one, the practice exam, and that is the remaining topic. The only one remaining topic that we haven't mentioned, but it is still on the exam, is about the Gaussian quadrature rule. And then you need to know how to use the Gaussian quadrature rule to approximate the integral, and that's it. And there's another question here, the question A. Approximate this integral by the Gaussian quadrature rule with the 2 Gaussian multipliers. And if you take a look at here, this question is set 1 is with the integral -1 and 1, and this is the standard one. And this one is not quite standard. Is the interval is from the -3 and 3, which means that you need to do some change of variable here. And today we are going to learn how to get the Gaussian quadrature rule. And also next class, I will tell you how to apply that Gaussian quadrature rule to finish these two questions to get the observations. Maybe I will get these two as the two examples in the class as well, so that you know how to do it. So now let's get back to what we have. On the iPads. Okay, good. So let's do some review first. Review on the things we have learned about the quadrature rule. And we have learned some things about the Crenshaw's.
Recording in progress.
There's some echo here. Got it. And as we mentioned before, and then maybe sometimes the equally distributed node points does not work pretty well. And then we get last time we get the Crenshaw's one, and then the Crenshaw's one looks like this. Where's the Crenshaw's one? The Crenshaw's node points, it looks like this, and then we get more things, more node points close to the end of the interval. And then this is the definition of the Chebyshev's node point, and this is the Crenshaw's Curtis quadrature rule. And the benefits of this is to get fast convergence. So I need to point out that this one, the Crenshaw's Curtis, this one is to get fast convergence results. And this one, we have fast convergence, and there's another question here. And can we get a higher accuracy quadrature rule? Yes. And also one of the benefits of this quadrature rule, you will learn later on, this quadrature rule, you can compute the coefficients with the fast Fourier transform. So the computations process is very efficient. And if you take a look at what we have, we are going to learn today, and then the Gaussian quadrature rule is not as efficient as this one. If we want to calculate the coefficients, all the coefficients here, we have to calculate the coefficients here, and then we need to calculate the node points here, and then the node point is just a cosine things here. So the calculation here, the computation is quite efficient, and it has a fast convergence. But why do we need the Gaussian quadrature rule? The Gaussian quadrature rule has its own benefits. So let's go to the Gaussian quadrature rule. This is something related to another interpolations. So let's see. I'm going to write down here. I'm going to write down, conclude some benefits here before we go into the details of the Gaussian quadrature rule. And first, we have already learned the trapezoidal, right? Trapezoidal rules. It could be like composite one, and then also the composite Simpson's rule as well. And these are very easy to apply. Easy to apply the rules, but not efficient, which means that, but not very accurate, scheme. This is not very accurate or low convergence. And so people come up with the Crenshaw-Curtis Crenshaw-Curtis scheme, and then this one has Bose convergence. And the coefficients can be calculated. The coefficients and the nodal voice are easy to calculate. It's easy to compute. And so this is the two benefits of it. And one thing I want to point out is that we use the interpolation here for the Crenshaw-Curtis, and what is it? Chebyshev interpolation. This is the interpolations we use in the Crenshaw-Curtis. So today we are going to get the Gaussian quadrature through. And let's take a look at its benefit. And it can achieve the highest accuracy, the highest order of accuracy, highest degree of accuracy, and there's no more benefits, sorry. It's not that if you take a look at the details, and then you will find out that the nodal points is not so easy to calculate, to compute. It asks you to solve some polynomials to get the nodal points. But actually people just keep that nodal points in record and then to do the calculations. I think this is the only benefit to achieve the highest accuracy, the degree of the accuracy. And let's see, there's one more thing I want to point out here. That is the nodal points we are using here. The nodal points is the Legendre type. And the Legendre type, and then I would mention later on, and then it is not the equally distributed one. But this two is the nodal points are equally distributed. The nodal points here. Nodal points are equally distributed. And this is the comparisons between all these methods we learned for the numerical integrations approximation. And so let's see, this is the comparisons part. And then I'm going to go into the details to see what we have for the Gaussian quadrature root. Although I mentioned that it's not so efficient, but nowadays, actually, most of people are going to use this one. Because the nodal points is really difficult to calculate at first, but you can just keep it in record and then use it to any interval once you get the nodal points. And people usually just use like 4 nodal points, 2 nodal points, 3 nodal points to get the as accurate as we can the approximations. And so here we are going to take a look at what we have today. And this is the Gaussian quadrature root. And this is not a Gaussian quadrature root. This is the equally distributed root scheme. And this is the normal one, and then is the one we use to derive the. Let me see. It's the one we use to derive the general interpolatory quadrature root. So the idea is we have the nodal points, a bunch of nodal points, and then we are going to do some language interpolations between among this node points, and then this is the Lagrange interpolation and fxj, and then this is the basis function. And we do the integrations on the interval a and b, and at the end of the day, we got this. So we are going to do the integrations on this part, which means that we have, so I'm going to do the calculations again, since in my office hour, and then some people just get confused, what is this? And so if we going to do the integrations of the Pn1 minus 1, this is the n minus 1 degrees of the interpolation. And if I do the integration, and then what can I get? And I get this. This is just a constant. This part is just a constant because this is the value, a function value at a node point. And this is a function, basis function LJX. And if I'm going to do the integration, and what things I get here is just so I can move the summations out, and then I can also get the this constant out. And the integration is all about the basis function. And if you take a look at here, there's another Wx here. This is just the wave function, and then you can skip it, ignore this parts, because usually we just use the wave function, Wx equals to 1, and then that's what we have here. Got it? And so what we have here is just the sigma sum, this part, and then fxj, and then this is the aj. This is the aj. So I would just copy this things here. N minus 1. This is actually the aj we defined there, but with the this part is just the aj, where the wave function Wx equals to 1. And that's it. And this is the idea of the interpolatory quadrature truth. And I'm going to prove this. So the degree of precisions, I'm going to erase this part and then guide you to prove this theorems step by step. Maybe it could be on the exam. I don't know. Would it be too complicated? Would it be too complicated for the exam? Yes or no? Yes, and then it could be on the exam. No, and then it could not be on the exam. Maybe you can answer my questions later on. And we are going to prove the degree of the precisions of the interpolatory quadratures. This is the 1, and then it's less than the 2n. And which means that the highest degree of the precisions can achieve by this quadrature truth, this interpolatory quadrature truth, that is 2n minus 1. This is the highest degrees of the accuracies we can achieve. So we are going to prove this first, and then the map is the map of this class is that, okay, first we prove this highest degree of the accuracy of this quadrature truth. It could be 2n minus 1. And then we are going to create the quadrature truth. Quadrature that has the degree of accuracy 2n minus 1, and that's it. That's the things we are going to get today and on Wednesday. And for this quadrature truth here, this is just the Gaussian's quadrature truth. So first, let us prove this. The highest degree of the accuracy we can achieve is 2n minus 1, and this is the theorem we have here. First of all, this is the whole proof. And if you think this is easy to memorize, and then you want it to be on the exam, and then you can tell me, and then it could be one of the questions on the exam, there's no change because like this is the theorem and then you want to prove it and then you just need to memorize all the things. And so now, so it depends on you if you want to calculate something, compute something, and then that's the things on the exam. And then if you prefer to memorize the proof, and then that's the thing. So you can vote for it after the class. So first, we are going to prove the degree of precision of the interpolatory quadratures is less than n and to n. And then if you remember what is the definitions of the degree of the precisions, and we can plot in the x and then to the, so which means that it's accurate up to this polynomial. So which means that if we plot in the fx equals to the x to the 2n minus 1, and then this quadrature rule is exact. And then if we plot in the polynomial, which is 2n, and then this is not exact, the not exact for this polynomial here, the degree here. And if we do some plotting here to this quadrature rule, and then this one is not exact. And so the idea is here. And let's go to take a look at, so we are going to do some proof by contradictions. This is the definition of the degree of precisions. So let's do the proof by contradictions. Proof by contradiction, this is something you learn in the Math A. The Math A tell you how to do the proof by contradictions. So you, first of all, you need to assume the conclusion is not correct, which means that this one, conclusion is that the degree of precision is less than 2n. And now you are going to assume that, okay, so assume this is not true, then the degree of precision is equals to or greater than the 2n. And so let's see, let's do some assumptions here. Suppose we have, suppose the degree of precisions of 1 is equal to or greater than greater than 2n. So this is the assumption, and let's take one polynomial here. This is a special polynomial we have. Let's see, take this polynomial and then take the polynomial, fx, and then this is a special case. And then this special case is defined with how many notable points do we have here? And then we have like the notable points x0 and then to the xn minus 1. And I'm going to create one polynomial by using the this notable points here. And then we have at the end we have the xn minus 1 and then doing the square here. And what's the degree of this precision of this polynomial? And this polynomial has degree. How many degree do we have here? So for the first item, and then this one, it is, you can write this one out, and then it's just the x squared, and then plus the x0 squared, and then minus 2x0 and then x. So for this part, this one has the degree of 2, right? And then you have degree of 2 here, and then degree of 2 here. How many items do we have here? We have 8 items that are with degree of 2. So which means that 2 degree, and then 2 degree, and then we have n items here, which means that this polynomial we have 2n degree. Does it make sense? So here we have degree of 2n. And what I just mentioned here, what I just mentioned is is the degree of the precision's definitions, right? The definition here I just mentioned. So if the degree of the precisions is 2n minus 1, so here if the degree of precision is 2n minus 1, then it's exact for the x to the 2n minus 1, and then for the 2n, and then it should not be exact. Not exact, because this is a degree of precision's definition. If the degree of precision is equals to 2n minus 1, which means that it's exact for this polynomial, but not exact for the degree of 2n polynomial. And so now we have such an degree of 2n degree polynomial. And now let's plug in this polynomial to that quadratic rule. And let's see, what do we have for the quadratic rule here? We have, first of all, we are using this to approximate. We are using this to approximate the integral fx, and then integrate on the AB. And then if the degree of precision here, if this is exact, which means that the blue part, if this is exact, and then which means that if we do the plotting here, and then this part should equals to this part. And so now let's do some plotting here to take a look at the left-hand side, and then also take a look at what we have on the right-hand side. And so for the left-hand side, on one hand, what we have is on one hand, and then we have the FAB, FX, and then DX, and then what we have here is AB and then x0 square, and then xn minus 1, and then square, and then dx. And this one should be bigger than 0. Does that make sense? Because this number, this function is non-negative, and then it also has some positive values in the interval, right? If you take a look at this function, I'm not sure how to draw that function, but I know this function is non-negative. I hope you can see this. And so for example, this is A and this is B, and then we have the x0 here, x1, x2, and then this is xn minus 1, xn minus 2. And if you take a look at function, and for this point, and then we have 0, and then for this point, we have a 0 value, right? Because for the definition there, if we plug in x equals to x0, and then this value is just 0. And then if we plug in x equals to x1, and then we get 0. So fx1 is also fx1 is also the 0, 0, 0 here, 0 here. And then in the interpolation here, there's some things in between, and then there's something in between, it should be positive. It could be, looks like this, but it could be more oscillatory because we have 2n degree. And which means that if you are going to do the integration, it should be positive about it. Because the area, it should be positive between the area between the curve and the x-axis, it should be positive. So we have this. And let's see what we have for the quadratic rule. That is the part we have here. This is the quadratic part, the quadratic rule part. And on the other hand, what do we have? We have this. We have, let's do the calculation. The quadratic rule formula, and then it equals to sigma n minus 1, j equals to 0, aj, and then fxj. This is the things we have here. Sigma sum n minus 1 fxj, aj, right? The aj is just a coefficient, and then it's the integration of that polynomial. but it doesn't matter. But let's take a look at this value. This is the important things here, fxj, which means that if we plug in xj, any index j could be from 0 to n-1. So let's see, if we plug in x1 and then we get a 0, and then we plug in x0 and then this one is still 0, the value. So if we plug in, replace the j with n-1, and which means that we have x equals to xn-1, and then this part is 0, and then which means that the f function value is also 0. This means that fxj always equals to 0. This part, fxj equals to 0 for any j equals to 0 to n-1, and which means that on the right hand side, and that is from the quadratus rule formula, and then it equals 0. Do you see the contradictions here? Yes. On the left hand side, you have positive value, and now on the right hand side, the quadratus rule gives you the 0. This is the true solution, and this is the approximation, and which means that the approximation is not exact here because they don't equal to each other, and this means that okay, your assumption is not quite true, and there's so the true value of the integration does not equals to integration does not use another color here, does not equals to the quadratus rule results. And this is a contradiction. This is a contradiction, and which means that we have the degree of precision should be less than that. Degree of precision should be less than 2n. And that's it. That's the things we want to conclude here. And that's the theorem. So now I want to ask, is this proof easy or difficult? If you think it's easy, and then it could be on the exam. It's like some free credits. If you just memorize every part and then nothing is changed. But some questions on the practice exam, I would change some value. You need to adapt the things. So this is the part you need to. The important things here is to get this polynomial. Create this polynomial, this special polynomial, and then do the plotting here and find out the contradiction. So this is the very important component in this proof. So now we have finished this part. The highest possible degree of accuracy of the quadratus rule is 2n-1 because it says it should be less than 2n, and then which means that the highest degree of precision is 2n-1. And we finish this. And the next part is to construct such a quadratus rule, and which has the degree of accuracy 2n-1. And now, this is just some things about the trapezoidal rule. And so here we have, let me see. So there are some pictures here, and for the first part, this is one function, this is another function, this is another function, and for here, I present the trapezoidal rule here, and to approximate the integral of the function fx. And if you take a look at here, and then the a and b, the for the trapezoidal rule, we choose the left endpoint and then right endpoint. And these two nodal points to be nodal points for the trapezoidal rule. And if you take a look at here, this is the area part, right? If you do the subtractions, this is the area between the function fx and their x-axis. And then this area, it represents the this part, and then this part, and then it represents the integral of the fx. And this part, the purple part, is just representing the trapezoidal rule result. So if you do the subtraction, the green part is the area. And we also have the error part here, and then this is the curve, and then between this line, and then this is the error part, and this error part is this part, and then and with this part. And let's see. So the nodal points, it looks like this. And if we choose other nodal points, but still using the trapezoid things, use the trapezoid area to approximate it. So I'm not going to choose the AB to be my nodal point for that trapezoidal rule. And here I use the x1, x2, it's inside the interval. And if you compare what we have there, and then you will see we have a smaller area for this part. Smaller area, although we have some small things here as well. But if you compare this part and then to that part, and then this part, the area part to that part, and then the area is actually become smaller. And so now our question is that how to choose this upper nodal points to get smaller area. And that's the Gaussian quadrature rule. And so they are not equally spaced, and then but this is still the quadrature rule, and we are going to use the coefficient Ci, and then also the values at the nodal points, and then doing the sigma sum, and then that's the Gaussian quadrature rule. But the question is that how to choose that xi, and I'm going to show you something here. This is something you have already done in the exercise. We have already stating that. I'm going to just show you all the things I have here. And let's say we have the x1 and x2, and that's what we have here. And then we want to choose the x1, x2 to get as accurate as we can. And so with two nodal points, how much accuracy can we get? The highest accuracy we can get is, let's see, I think I have something here. It should be, here we have n nodal points, right? For this one, we have, although the numeration here is n-1, we have n more nodal points, right? And then the accuracy is 2n-1.
For the error, can you scroll down to the trapezoidal?
Mm-hmm.
Is the error like for the bottom left? Is it the green plus the red, or the green, the absolute value of the green?
So here, if we want to do the subtractions, it should be this part, right? And then subtract the purple part, right?
So the error.
So it should be
the
this
green
part and then minus this one.
the absolute value of the error.
Yeah, yeah. But it's still like smaller than that part, the trapezoidal rule. But this one is with the other nodal points. So now we want to get the highest accuracy we can. And for this, from this theorems, which means that I need to point out that because the index here is a little bit confused, and then I want to point out that, so with n nodal points, and then we can get at most 2n-1 degrees of precision. So let's forget about the index here. So the index could be starting from the 1, and then sometimes the index could be starting from 0. But we can make sure that one thing we can make sure is that with n node points, and then we can get at most 2n minus 1 degree of precisions. So let's get back to that problem, because sometimes the index could be confusing. Sometimes the index, node points could be start with 0. Sometimes it begins with 1. But here, this question is beginning with 1. But it doesn't matter how many node points do we have. We have 1 node points, we have 2 node points, and which means that what is the highest degree of precision we can achieve? We can have 2 times 2 minus 1. This is the number of node points we have, right? 2n minus 1. And this is the highest degree of the node points, degrees of precision we can get. Which means that by the definition of the degree of precision, which means that this quadratic rule can be except for this polynomial. This polynomial is a degree of 3 polynomial, and the basis function is just the 1 and then x and then x squared and x3, and we can do such a plug in here to get the x1 and then x2, x1 and x2. X1 and then X2 and then C1 and then C2 value here. So we can determine that C1, C2, X1, X2, and because we can plug in this polynomial to get the linear system of equation. And because I just mentioned for this function, we can view it as a linear combination of the the basis function, a linear combination of the 1 and the x and the x squared and the x cubic, this 4 functions here, 4 polynomial here. Which means that, okay, because we have this degree of precision 3, and then the quadratic rule could be except for such 3-degree polynomials. And this 3-degree polynomials is the linear combinations of this 4 basis function. And now we are going to do some plug in here for that quadratic rule. This is the quadratic rule. And then we want to find out the C1, X1, C2, X2, such that this quadratic rule has the highest degree of precision. So now, this is the things. This is the quadratic rule. I'm going to do some plug in here. And this is the first basis function, fx equals to 1, and then the second basis function, fx equals to x, and the third basis function, x squared, and then this is x cubic. And how do I do the plug in here? For the left-hand side, and then I'll just plug in the 1 here, and then do the integration, and the same thing happening to the second case, third case, and the fourth case. And I just do the plug in for the fx, and then do the integration, and then I get the value. And then on the right hand side, I'm going to do the same plug in here, and then this is fx equals to 1, which means that the fx1 equals to 1, fx2 equals to 1 as well. And so 1 here, c1 times 1, c2 times 1, and then I get c1 plus c2. And for the fx equals to x, this is second case on the right hand side. And because this is the function x, which means that f evaluate at x1 with the function x, and then it's just x1. And then for the function fx equals to x, and then evaluate at x2, and then that is the x2 here. This makes sense? So here for the square, and then I get square. For the cubic, I have cubic here. And that's a nice things. We have 4 equation. If you take a look at here, the blue part. This equals to C1 plus C2. This 0 equals to C1 times X1 plus C2 times X2. And I have 4 equation. And then I have 4 equation, and I have 4 variable. What C1, C2, X1, X2. And with 4 equation, 4 unknowns, and then I can solve for the C1, C2, X1, X2. And it's actually difficult to solve it by hand. And here I use the computer. You can use the Python every time. This is not linear algebra class. I'm not asking you to solve the polynomial by hand. Use the Python. This is numerical methods. Use a computer. Numerical method, which means that use a computer. Okay, use a computer, and then we can solve for C1, C0, and then A equals 1. And this is negative square root of 3 divided by 3. This is the square root of 3 divided by 3. This is another voice. These are the delta voice, square root of 3 over 3, and then negative square root of 3 over 3. And this is the quadratic rule. C1 is here, but I just keep writing the C1 because it is just 1, and this is just 1. And this is the Gaussian quadratic rule on the interval -1 and 1 with two node voice. Does that make sense? You can create the Gaussian quadratic rule by solving the linear system of equation. There is another general things about the Gaussian quadratic rule. And at the end of the day, you will find out that all these node points could be a solutions to the Legendre polynomial. And this is the another part. And I need to talk about the next part on Wednesday. I'm going to show you something first. So this is one way to get the Gaussian quadratic point and the Gaussian quadratic coefficient by solving, putting in the polynomials here, right? And at the end of the day, let's just focus on the standard integrals. The interval is -1 and 1. And at the end of the day, I would give you some results like this. That's why people use this, because people memorize what we have. So let's see, there's one table, and I got two tables here, but okay. This is some tables people use to apply the Gaussian node points. And if you take a look at the table here, and these are the node points, and if we have two node points, and this is the square root of 3 divided by 3, that is just what we get. This is the negative square root of 3 divided by 3, and this is the node points, and then these are the coefficient. They are fixed for each interval -1 and 1, and then you just can apply it to different function at x. And these are all the node points for the interval -1 and 1. But this one is with 3 node points, and then for different node points, and then it has different coefficient. These are the 4 node points, and these are the 5 node points. But as you can see, you need to solve the equation, and then that's so complicated. If you want to get more node points, and that's too hard to solve the things. It could be like 50 degrees of the polynomials, and then you need to solve that things. So most people just use up to like 5 node points. No one use like 15 node points. I try it, and then it takes me like 1 hour, and then the computer cannot solve it. Yeah, that's the things, and then we will talk about the node points next class.